Tonight, we're going to take a slow and quiet journey through the periodic table. Not as something to memorize. Not as a chart full of symbols, numbers, and classroom pressure. But as a gentle map of matter itself. A soft, organized map of the tiny building blocks that make up water, air, stone, metal, stars, oceans, trees, and even the cells inside your body. You don't need to remember every element tonight. You don't need to study. You don't need to solve anything. You can simply listen. And if your mind begins to wander, that's completely okay. This is not a lesson you need to hold tightly. It is just a calm walk through chemistry, one small idea at a time. So let your body settle. Let your shoulders soften. Let your breathing become slower. And imagine, for a moment, a dark and quiet room. In front of you is a glowing table. Rows and columns of little boxes. Each box holding the name of an element. Hydrogen, carbon, oxygen, gold, iron, neon. Some of these names may feel familiar. Some may feel strange. But every one of them is part of the same quiet story. The story of what everything is made of. Welcome to Gentle Chemistry. Tonight, we're exploring the periodic table, slowly and softly, before sleep. At first glance, the periodic table may look complicated. It has many boxes, many letters, many numbers. There are rows, columns, colors, symbols, and names. It can feel like something from a classroom wall. Something you were supposed to memorize. Something that belonged to tests, textbooks, and long school days. But if we look at it more gently, the periodic table becomes something much more beautiful. It becomes a map. Not a map of countries. Not a map of roads. But a map of matter. A map of the ingredients of the universe. Everything around you is made from combinations of these elements. The glass in a window. The salt in the ocean. The oxygen you breathe. The carbon in your skin. The iron in your blood. The calcium in your bones. The gold in a ring. The helium inside some balloons. The sodium and chlorine inside table salt. The silicon inside sand. The nitrogen in the air. All of these come from the periodic table. And that means the periodic table is not just a scientific chart. It is a quiet inventory of the physical world. A list of nature's basic materials. A little like a library, where every element is a book. Or a set of musical notes, where every element has its own sound. And when those notes combine, they create the endless music of chemistry. Before we talk about elements, it helps to think about matter itself. Matter is anything that has mass and takes up space. A stone is matter. A cloud is matter. A drop of water is matter. The air moving slowly in and out of your lungs is matter too. Some matter feels solid and heavy. Some matter flows. Some matter is invisible. Some matter is soft, like mist. Some matter is hard, like crystal. Some matter burns. Some matter shines. Some matter quietly holds its shape for thousands of years. But underneath all of it, there are atoms. Atoms are the tiny pieces that make up ordinary matter. They are far too small to see with your eyes. Even a single grain of sand contains more atoms than the mind can comfortably imagine. And yet, these tiny atoms are not random. They follow patterns. They have structure. They combine in certain ways. They separate in certain ways. They form the world you can touch, smell, taste, and see. Chemistry begins when we start paying attention to these tiny pieces, noticing how they connect, how they rearrange, how they become water, salt, sugar, metal, air, stone, wood, and life. So before the periodic table is a table, it is a quiet answer to a very old question. What is everything made of? To understand the periodic table, we can begin with a very simple question. What is an element? An element is a pure kind of matter made from only one type of atom. That may sound small. And it is. Atoms are incredibly tiny. So tiny that we cannot see them with our eyes. But they are the foundation of chemistry. If you could zoom in closer and closer on any object around you, you would eventually reach the world of atoms. A wooden table. A cup of water. A stone. A candle flame. A leaf. Your hand. Everything is made of atoms. And an element is defined by what kind of atom it has. Hydrogen is made of hydrogen atoms. Oxygen is made of oxygen atoms. Gold is made of gold atoms. Carbon is made of carbon atoms. Each element has its own type of atom. And what makes one atom different from another is something hidden deep inside it. At the center of an atom is a tiny nucleus. Inside that nucleus are particles called protons. The number of protons is what gives an element its identity. Hydrogen has 1 proton. Helium has 2. Lithium has 3. Carbon has 6. Oxygen has 8. Gold has 79. This number is called the atomic number. And on the periodic table, the elements are arranged by this number, one by one. From the simplest atom, hydrogen, all the way to much heavier and more complex atoms. So, in a way, the periodic table is a list of atoms arranged by the number of protons in their hearts. A quiet staircase of matter. 1 proton. 2 protons, 3 protons, and onward. Now, atoms do not always stay alone. Often, they join together. When atoms connect, they can form molecules. A molecule is like a tiny arrangement of atoms, held together by chemical bonds. Water is a molecule. Oxygen in the air is usually found as a molecule made from 2 oxygen atoms. Carbon dioxide is a molecule. Sugar is made of molecules. The scent of a flower comes from molecules drifting through the air. The taste of chocolate comes from molecules touching receptors on your tongue. The freshness of rain after a dry day comes from tiny compounds released from the ground and carried through the air. So the periodic table does not only tell us about single atoms. It gives us the letters that can be combined into chemical words. Hydrogen and oxygen can become water. Sodium and chlorine can become salt. Carbon, hydrogen, and oxygen can become sugar. Carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur can become the chemistry of living things. This is one of the reasons the periodic table is so powerful. It is simple, but it can create complexity. Like an alphabet. There are only a limited number of letters. But those letters can become poems, stories, songs, names, and entire libraries. In the same way, the elements become the language of matter. And chemistry is what happens when that language begins to speak. underscore 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 underscore. Let's begin at the very first element. Hydrogen. Hydrogen is the simplest element. It has one proton. It is light, simple, and ancient. In fact, hydrogen is the most common element in the universe. Long before Earth existed, long before oceans, plants, animals, or people, there was hydrogen. Stars are filled with it. The early universe was filled with it. And inside stars, hydrogen atoms are pressed together under enormous heat and pressure. They fuse. They release energy. And they help stars shine. So the first little box on the periodic table, hydrogen, is not just a symbol. It is connected to starlight. It is connected to the beginning of matter. It is connected to the quiet glow of the universe. Hydrogen also appears in water. Each water molecule has 2 hydrogen atoms and 1 oxygen atom. H2O. A simple formula. 2 hydrogens. 1 oxygen. Together, they create something that flows, freezes, evaporates, forms clouds, fills rivers, and makes life possible. A tiny element from the stars becomes part of a raindrop. That is the kind of story hidden inside the periodic table. Next comes helium. Helium has 2 protons. It is also very light. You may know helium from balloons, but helium is much more than that. Helium is a noble gas. That means it is very calm, chemically speaking. It does not easily react with other elements. It prefers to stay by itself. There is something peaceful about that. Helium is stable, quiet, complete in its own way. It floats upward because it is lighter than air. And it is also formed inside stars. When hydrogen atoms fuse together, helium is one of the products. So helium is also part of the chemistry of stars. A silent, light element. Floating. Glowing. Resting in the second box of the periodic table. As we move through the table, each element gains more protons. Lithium has 3. Beryllium has 4. Boron has 5. Carbon has 6. And carbon is one of the most important elements for life. Carbon is special because it can bond with many other atoms. It can form long chains, rings, branches, complex shapes. This makes carbon incredibly useful for building the molecules of life. Your body contains carbon. Plants contain carbon. Food contains carbon. Wood, sugar, protein, DNA, and oils all contain carbon. Carbon can be soft and dark as graphite, the material in a pencil. But carbon can also become diamond. Clear, hard, and sparkling. The same element. Different arrangement. Different structure. Different world. This is one of the quiet wonders of chemistry. Sometimes matter is not only about what atoms are present. It is also about how those atoms are arranged. The same carbon atoms can become something ordinary, like pencil graphite. Or something precious, like diamond. Chemistry is full of these gentle transformations. The same building blocks. Different patterns. different properties, different stories. Now let's look at nitrogen. Nitrogen has 7 protons. It makes up most of the air around you. Every slow breath you take is mostly nitrogen, mixed with oxygen and small amounts of other gases. Nitrogen is quiet in the atmosphere. It exists as pairs of nitrogen atoms, strongly bonded together. Those bonds make nitrogen gas very stable. It drifts around us all day and all night, invisible and calm. But nitrogen is also essential for life. It is part of proteins. It is part of DNA. It helps build the chemistry inside living cells. Plants need nitrogen to grow. Animals need nitrogen because their bodies are made of proteins. The living world depends on nitrogen moving through cycles. From the air, to the soil, to plants, to animals, and back again. So nitrogen is both quiet and essential. It surrounds us invisibly. It rests in the air. And it also helps build the living structure of the world. Now let's look at oxygen. Oxygen has 8 protons. You know oxygen because you breathe it. Every slow breath you take depends on oxygen. The air around you is mostly nitrogen, with a smaller but essential amount of oxygen. Your body uses oxygen to release energy from food. Fire uses oxygen too. When something burns, oxygen takes part in the chemical reaction. That is one reason fire feels so alive. It glows. It moves. It consumes. But underneath that dancing light, there are atoms rearranging, bonds breaking, new bonds forming, energy being released. Oxygen is also part of water, part of rocks, part of the atmosphere, part of countless molecules around us. It is a quiet but powerful element, and on the periodic table, it rests in its own little box. One symbol, one element, but connected to breath, water, fire, stone, and life. And if some of these names begin to blur together, that is perfectly fine. You do not need to hold them all in your mind. Hydrogen, helium, carbon, nitrogen, oxygen. They can simply pass by like soft lights in the dark. The important thing is not to memorize them tonight. The important thing is just to feel the pattern. Each element has a place. Each element has a number. Each element has a personality. And together, they create the matter around us. The periodic table is arranged in rows and columns. The rows are called periods. The columns are called groups. The word periodic means that patterns repeat. And that is the great secret of the periodic table. It is not random. It is full of repeating patterns. Elements in the same column often behave in similar ways. They are like members of a chemical family. They have similar habits, similar tendencies, similar ways of bonding. This pattern comes from electrons. Electrons are tiny negatively charged particles that exist around the nucleus of an atom. They are not exactly like little planets orbiting a sun, even though that is the picture we often imagine. The real world of electrons is stranger, softer, and more mathematical. But for tonight, we can think of electrons as forming layers around the atom. These layers are sometimes called shells. The outermost electrons are especially important in chemistry. They help decide how atoms bond, react, share, give, or receive. Atoms are often most stable when their outer electron shell is full. Some atoms want to give away electrons. Some want to gain electrons. Some share electrons. And this is where chemical bonding begins. The periodic table is arranged so that elements with similar outer electron patterns line up in columns. That is why elements in the same group behave similarly. The table is not only arranged by size, it is arranged by behavior, by pattern, by the hidden structure of atoms. The periodic table is like a piece of music where the same themes return again and again. Each row brings new elements, but the columns carry repeating chemical rhythms. Reactive metals, calm noble gases, halogens, alkaline earth metals, transition metals, patterns within patterns, a quiet order beneath the surface of matter. Let's look at some of these chemical families slowly. On the far left side of the periodic table are the alkaline metals: lithium, sodium, potassium, rubidium, cesium, francium. These elements are soft metals. They are reactive. They are eager to give away one outer electron. Sodium is one of the most familiar alkaline metals. By itself, sodium is a soft, silvery metal that reacts strongly with water. But in everyday life, we usually need sodium in a calmer form, as part of table salt. Table salt is sodium chloride, sodium and chlorine, NaCl. Alone, sodium is highly reactive. Chlorine, by itself, is a greenish gas that can be dangerous. But when sodium and chlorine come together, they form something familiar: salt. Tiny white crystals. Something we sprinkle on food. This is another quiet lesson from chemistry. Elements can have strong and even dangerous personalities by themselves. But when they combine, they can become something completely different. A metal and a gas can become a crystal. A reactive atom and another reactive atom can settle into balance. Chemistry is the art of rearrangement, the art of becoming something new. Next to the alkaline metals are the alkaline earth metals: beryllium, magnesium, calcium, strontium, barium, radium. These elements are also metals, but they are generally less reactive than the alkaline metals. Calcium is one of the most familiar. It is found in bones and teeth. It is found in seashells. It is found in limestone. It is part of the hard structures that living things build. When you think of calcium, you might think of strength. Bones, shells, stone. But calcium is also involved in subtle processes inside living cells. It helps with signaling. It helps muscles contract. It helps nerves communicate. So calcium is not only a material of hardness. It is also part of movement, life, and communication. A quiet metal hidden in the body. A soft symbol on a table. Ca. One little box, connected to bones, shells, stone, and living motion. In the center of the periodic table are many transition metals: iron, copper, nickel, silver, gold, zinc, titanium, platinum. These elements often feel familiar because humans have used them for thousands of years. They can be strong, shiny, malleable, conductive, useful. Iron is one of the most important metals in human history. It is found in tools, buildings, machines, bridges, and inside your blood. In your body, iron helps carry oxygen. A tiny amount of iron inside hemoglobin allows your blood to transport oxygen from your lungs to the rest of your body. So iron is both ancient and intimate. It is in the earth. It is in industry. It is in the red color of blood. It is part of planets, tools, and life. Copper is another transition metal. Warm in color. Able to carry electricity. Used in wires, pipes, coins, and old roofs that slowly turn green with time. Silver is bright and reflective. Gold is soft, heavy, and resistant to corrosion. Gold does not easily tarnish. That is one reason humans have valued it for thousands of years. It keeps its warm yellow shine. Gold appears in jewelry, coins, electronics, art, and ancient treasures. On the periodic table, gold is simply O. 2 letters. But behind those letters is a long human story. Beauty, wealth, alchemy, trade, desire, and the strange fascination humans have always had with matter that does not fade. On the right side of the table, before the noble gases, are the halogens. Fluorine, chlorine, bromine, iodine, astatine, tennessine. The halogens are reactive nonmetals. They often form salts when they react with metals. Chlorine is the one many people recognize. It is part of sodium chloride, table salt. It is also used in certain forms to disinfect water. Iodine is another halogen. It is important for the body in tiny amounts, especially for the thyroid gland. Bromine is a reddish-brown liquid at room temperature. Fluorine is extremely reactive. Each halogen has its own personality. But they share a family resemblance. They tend to need one more electron to complete their outer shell. That desire shapes their chemistry. Again, the periodic table is showing us behavior. Not just names. Not just numbers. But tendencies. Patterns. Quiet chemical habits. And then, at the far right of the table, are the noble gases. Helium, neon, argon, krypton, xenon, radon. These elements are known for being very unreactive. They usually do not form compounds easily. They are chemically quiet. Neon, for example, is used in glowing signs. When electricity passes through neon gas, it can glow with a beautiful light. But chemically, neon is calm. It does not want to bond much. It is like a person sitting peacefully at the edge of a room, content to be alone. The noble gases are complete in a certain way. Their outer electron shells are full. And because of that, they do not need much from other atoms. They are stable, still, quiet. There is a kind of sleep-friendly poetry in the noble gases. They remind us that not all matter is restless. Some atoms are already at peace. Some atoms do not need to reach outward. Some simply glow under the right conditions, then return to stillness. Between metals and nonmetals are the metalloids. Elements like silicon, boron, arsenic, antimony, and tellurium. They sit near the staircase-like line on the periodic table. They have properties somewhere between metals and nonmetals. Silicon is especially important in the modern world. It is found in sand and quartz. It is used in glass. It is also essential in computer chips. So silicon connects ancient Earth to modern technology. It is in beaches. It is in windows. It is in the tiny circuits inside phones and computers. Silicon shows how one element can belong to many worlds at once. A mineral world, a glass world, a digital world. And all of it begins with a small box on the periodic table. C. Silicon. Quiet, abundant, and deeply important. Before we move lower down the table, we can pause with a few more elements. Not because you need to remember them, but because each one shows how a small square on the table can open into a larger story. Let's begin with phosphorus. Phosphorus is an element connected to light, life, and energy. Its symbol is P. It is found in DNA. It is found in bones. It is found in the molecules that help living cells store and move energy. Inside your cells, there is a molecule called ADP. You do not need to remember its full name tonight. It is enough to know that ADP helps carry energy inside living things. And phosphorus is part of that quiet system. Every time a muscle moves, every time a cell works, every time life quietly continues, phosphorus is somewhere in the story. There is also something mysterious about phosphorus in history. Some forms of phosphorus can glow faintly in the dark. This made it seem almost magical when it was first discovered. A substance connected to bones, life, energy, and pale light. A small letter on the periodic table. Phosphorus. A quiet element with a strangely luminous past. Sulfur is another element with a strong personality. Its symbol is S. It is yellow in its pure solid form. It is found near volcanoes. It appears in minerals. It is part of certain amino acids, which help build proteins in living things. Sulfur can be associated with strong smells, especially in some compounds. Rotten eggs, hot springs, volcanic gases. But sulfur is not only unpleasant or dramatic. It is also important. It helps shape proteins. It appears in medicines. It appears in the chemistry of Earth. It has been known since ancient times. People notice sulfur because of its color, its smell, and the way it burned. In older stories, sulfur was sometimes linked with fire, transformation, and the underground world. It feels like an element from caves, volcanoes, and old laboratories. But at the same time, it is part of life. This is one of the strange things about chemistry. An element can feel harsh in one form and essential in another. Sulfur can belong to smoke and volcanoes. And it can also belong to the soft machinery of living cells. Copper is warmer. Its symbol is Cu. Copper has a reddish-orange glow. It has been used by humans for thousands of years. Long before modern electronics, people shaped copper into tools, ornaments, vessels, and coins. Copper is soft enough to work with, but useful enough to matter. It conducts electricity very well. That is why copper is hidden inside so many wires. Behind walls. Inside devices. Inside cables. It carries signals and power quietly, without calling attention to itself. Copper also changes with time. When exposed to air and moisture, copper surfaces can slowly form a green patina. You may have seen this on old roofs, statues, or monuments. The Statue of Liberty, for example, has that green color because of copper chemistry on its surface. The metal underneath is not green at first. Time and air create the color. So copper is not only a metal of wires and tools. It is also a metal of slow change. A metal that records time on its surface. Silver is bright and cool. Its symbol is Ag. Silver reflects light beautifully. It has been used in jewelry, coins, mirrors, photography, and decoration. When you think of silver, you might imagine moonlight. A cool shine. A quiet reflection. Like gold, silver has been treasured by humans for a very long time. But silver changes more easily than gold. It can tarnish. Its surface can darken when it reacts with sulfur compounds in the air. This tarnish is not the disappearance of silver. It is chemistry at the surface. A thin layer. A quiet reaction. A reminder that even shiny things are always meeting the air around them. Silver also has important uses beyond beauty. It conducts electricity very well. It has been used in photographic chemistry. It appears in electronics and specialized materials. One element can belong to art, money, light, memory, and technology. That is the periodic table again. Small boxes. Large stories. Neon is different. Neon is a noble gas. Its symbol is Na. It does not easily react with other elements. It is calm. It is stable. But when electricity passes through neon gas, it can glow. A bright, colored light. This is why neon became famous in science. City streets. Theater lights. Old storefronts. Glowing letters in the night. There is something almost poetic about neon. Chemically, it is quiet. But under the right conditions, it shines. It does not need to form complex compounds to be beautiful. It simply glows when energized. Like a silent element waking briefly into light, then returning to stillness. And then there is uranium. Its symbol is U. Uranium is heavy. Much heavier than elements like carbon or oxygen. It is found in rocks and minerals. It is radioactive, which means its atoms can slowly change over time, releasing energy from the nucleus. We do not need to go deeply into nuclear chemistry tonight. We can simply notice that uranium belongs to a different kind of story. A story of deep time. A story of Earth's interior. A story of energy hidden inside atoms. Most chemistry is about electrons and bonds. But radioactive elements remind us that the nucleus itself can also hold change. Uranium has shaped geology, energy, science, and human history. It is powerful. It is serious. And like many powerful things in chemistry, it needs respect. On the periodic table, uranium is just one square. But behind that square is a vast and complicated world. A heavy element. A slow clock. A reminder that atoms can carry energy not only in their bonds, but deep in their centers. And now, if those stories feel like many small lanterns passing by, you can let them pass. Phosphorus. Sulfur. Copper. Silver. Neon. Uranium. You do not need to keep them. Just notice how different they feel. Some glow. Some conduct. Some build life. Some smell of volcanoes. Some reflect light. Some carry deep energy. The periodic table is not flat when we look at it this way. It becomes a landscape. A quiet landscape of matter. With bright places. Heavy places. Soft places. reactive places, and calm places. Lower down on the periodic table, there are two separated rows. These are the lanthanides and actinides. They are often placed underneath the main table to keep the shape easier to read. The lanthanides include elements sometimes called rare earth elements. Despite that name, some are not truly rare, but they can be difficult to separate from one another. They are used in magnets, lights, electronics, and many modern technologies. The actinides include elements like uranium and plutonium. Some of these elements are radioactive. Uranium is heavy and complex. It is connected to nuclear energy, geology, deep time, and human history. We do not need to go deeply into nuclear chemistry tonight. But we can notice that the periodic table does not stop with familiar materials. It reaches into heavy elements, unstable elements, elements made in laboratories, elements that exist only for brief moments. The table holds both the ordinary and the strange, salt and gold, oxygen and uranium, calcium in bones, neon in science, hydrogen in stars, elements that feel close, and elements that feel almost like whispers at the edge of matter. The story of the periodic table is also a human story. For a long time, people knew about certain materials: gold, silver, iron, copper, lead, sulfur, carbon, mercury. But they did not know atoms the way we understand them today. Ancient people saw matter change. Wood became ash. Ore became metal. Water became steam. Wine became vinegar. Plants became medicine. They saw color, smoke, flame, crystals, and corrosion. But they did not yet know the tiny structures underneath. For centuries, alchemists tried to understand transformation. They searched for ways to turn base metals into gold. They searched for hidden principles in matter. They mixed, heated, distilled, and observed. Some of their ideas were mystical. Some were wrong. But they were part of the long path toward chemistry. Alchemy was not modern chemistry. But it carried a powerful question. How does matter change? How can something become something else? And that question never really disappeared. Modern chemistry still asks it, only with clearer tools and better explanations. Why does metal rust? Why does fire burn? Why does salt dissolve? Why does sugar caramelize? Why do leaves change color? Why do atoms bond? The periodic table eventually became one of the great answers. Not the only answer, but a beautiful one. A way to organize the elements behind all those transformations. Eventually, scientists began to identify elements more clearly. They measured gases, studied reactions, compared substances, named new materials, weighed them, tested them, separated them, and slowly the idea emerged that matter was made from fundamental elements. Then, in the 1800s, a Russian chemist named Dmitry Mendeleev helped arrange the elements into a table. He noticed patterns. When elements were ordered in certain ways, their properties repeated. Mendeleev's table was powerful because it did more than organize known elements. It also predicted elements that had not yet been discovered. He left gaps, quiet empty spaces, and later scientists found elements that fit those spaces. That is one of the most beautiful things about a good scientific pattern. It does not only describe what we know, it points toward what we have not yet seen. The periodic table became a kind of map with empty rooms waiting to be filled. And over time they were. There is something wonderful about those empty spaces. They remind us that science is not only a collection of facts. It is also a way of noticing patterns so carefully that the unknown begins to take shape. A missing element can become imaginable before it is found. A blank square can become a promise. A gap can become a clue. Now let's bring the periodic table closer to the room around you. Very close. Close enough that it no longer feels like a chart from a lab. Close enough that it feels like part of the quiet space where you are resting. It may seem like a scientific poster, but it is also in your bedroom right now. Oxygen and nitrogen are in the air. Carbon, hydrogen, and oxygen may be in the wood of a table or the cotton of a blanket. Silicon and oxygen may be in glass. Copper may be inside wires. Lithium may be inside a battery. Iron may be inside screws, tools, or furniture. Calcium is inside your bones. Phosphorus is inside your DNA. Sodium and potassium help your nerves send signals. Carbon is in your skin. Hydrogen is in water inside your body. Oxygen is entering and leaving with every breath. If there is a glass of water nearby, it is hydrogen and oxygen. If there is a window in the room, the glass is mostly made from silicon, oxygen, and other elements arranged into a transparent solid. If there is a phone beside you, it may contain lithium in its battery. It may contain silicon in its chips. It may contain copper, gold, tin, nickel, aluminum, and many other elements in tiny amounts. If there is a lamp, electricity may be moving through copper wires. If there is a blanket, it may contain carbon, hydrogen, oxygen, and nitrogen arranged in long soft fibers. If there is dust in the room, even that dust is chemistry. Tiny pieces of fabric. Minerals. Skin cells. Pollen. Carbon-based fragments of the everyday world. If there is a wall, it contains minerals and compounds. If there is paint, it contains pigments, binders, and solvents that once dried into a colored surface. If there is a book, its paper is mostly cellulose, built from carbon, hydrogen, and oxygen. If there is a candle, its wax is made from long chains of carbon and hydrogen. And when it burns, those chains react with oxygen, releasing light and warmth. Your own body is also a quiet periodic table. Oxygen, carbon, hydrogen, nitrogen, calcium, phosphorus, sulfur, sodium, potassium, iron, magnesium, zinc. Some are present in large amounts, some only in traces, but each has a role. Calcium helps give bones their structure. Iron helps carry oxygen in blood. Sodium and potassium help nerve signals move. Phosphorus is part of DNA and cellular energy. Carbon builds the backbone of living molecules. Oxygen helps release energy from food. Hydrogen is everywhere in water and organic molecules. So the table is not distant. It is around you. It is inside you. It is under your hands, in your breath, in your bones, in the quiet room, in the air, and in the objects resting nearby. The periodic table is not far away. It is not locked inside a classroom. It is not only printed on a poster. It is everywhere. In the cup beside your bed. In the lamp near the wall. In the window. In the dust. In the quiet movement of your breathing. In the chemistry of sleep itself. Everything nearby is a mixture of elements, arranged in different ways. Some arrangements are soft. Some are hard. Some are transparent. Some are living. Some are still. And this is why chemistry can feel so gentle when we look at it slowly. It is not only about reactions in a lab. It is about the quiet structure of ordinary things. The periodic table also connects Earth to the stars. And this part of the story can feel especially quiet, especially vast. Because when we look at the periodic table, we are not only looking at chemistry. We are looking at a memory of the universe. Many elements were formed in stars. Hydrogen and helium appeared very early in the universe. They are the ancient light elements. Simple. Abundant. Born near the beginning of everything. For a long time, the universe was mostly hydrogen and helium. Clouds of gas gathered under gravity. Stars formed. Inside those stars, pressure and heat became enormous. Hydrogen nuclei fused together. Helium formed. Energy was released. Light poured outward. A star began to shine. But stars do more than shine. They are also cosmic furnaces. Inside them, lighter elements can become heavier ones. Carbon can form. Oxygen can form. Neon. Magnesium. Zinc. Some are present in large amounts. Some only in traces. But each has a role. Calcium helps give bones their structure. Iron helps carry oxygen in blood. Sodium and potassium help nerve signals move. Phosphorus is part of DNA and cellular energy. Carbon builds the backbone of living molecules. Oxygen helps release energy from food. Hydrogen is everywhere in water and organic molecules. So the table is not distant. It is around you. It is inside you. It is under your hands, in your breath, in your bones, in the quiet room, in the air, and in the objects resting nearby. The periodic table is not far away. It is not locked inside a classroom. It is not only printed on a poster. It is everywhere. In the cup beside your bed. In the lamp near the wall. In the window. In the dust. In the quiet movement of your breathing. In the chemistry of sleep itself. Everything nearby is a mixture of elements, arranged in different ways. Some arrangements are soft. Some are hard. Some are transparent. Some are living. Some are still. And this is why chemistry can feel so gentle when we look at it slowly. It is not only about reactions in a lab. It is about the quiet structure of ordinary things. The periodic table also connects Earth to the stars. And this part of the story can feel especially quiet, especially vast. Because when we look at the periodic table, we are not only looking at chemistry. We are looking at a memory of the universe. Many elements were formed in stars. Hydrogen and helium appeared very early in the universe. They are the ancient light elements. Simple. Abundant. Born near the beginning of everything. For a long time, the universe was mostly hydrogen and helium. Clouds of gas gathered under gravity. Stars formed. Inside those stars, pressure and heat became enormous. Hydrogen nuclei fused together. Helium formed. Energy was released. Light poured outward. A star began to shine. But stars do more than shine. They are also cosmic furnaces. Inside them, lighter elements can become heavier ones. Carbon can form. Oxygen can form. Neon. Magnesium. Silicon. Sulfur. And in massive stars, the process can continue until iron. Iron is special because building elements heavier than iron by fusion no longer releases energy in the same way. So iron can be thought of as a kind of quiet boundary inside the life of a massive star. A heavy point in the story. And when a massive star reaches the end of its life, it may explode as a supernova. In that explosion, space is filled with newly made elements. The star scatters its chemistry outward. A cloud of enriched material spreads into the dark. Later, that material can become new stars, new planets, new oceans, new rocks, and eventually, living things. Some of the heaviest elements, including elements like gold, may be formed in extremely violent cosmic events, such as the merging of neutron stars. So a piece of gold is not only beautiful because it shines. It is beautiful because its atoms may carry the memory of an ancient cosmic collision. A ring. A tiny circuit. A fleck of golden rock. All of it points back to the sky. But heavier elements were created later, inside stars and during powerful cosmic events. Carbon. Oxygen. Silicon. Iron. Gold. Many of the atoms around us were born in extreme places. Inside stellar furnaces. During supernova explosions. In the violent merging of neutron stars. This means the periodic table is not only a table of chemistry. It is also a table of cosmic history. The calcium in your bones. The iron in your blood. The carbon in your cells. The oxygen you breathe. These atoms have old stories. Much older than Earth. Much older than life. They have passed through stars, clouds of gas, planets, oceans, and living things. Matter moves. It changes form. It becomes rock. Then dust. Then water. Then a plant. Then an animal. Then soil. Then something else again. Chemistry is the story of these transformations. And the periodic table is the alphabet. With these elemental letters, the universe writes everything. And this can make the periodic table feel less like a chart and more like a night sky. Each square is a star of meaning. Each symbol is a memory. Hydrogen remembers the beginning. Carbon remembers the inner lives of stars. Oxygen remembers breath and oceans. Iron remembers massive stars and the red color of blood. Gold remembers rare and violent cosmic events. Calcium remembers bones, shells, and ancient seas. Silicon remembers sand, glass, and stone. The table is a small rectangle of human order. But inside it is an enormous story. A story that begins in the early universe and continues in the quiet room around you. Let's imagine some of those elemental letters more slowly. Hydrogen is the letter of beginnings. Simple, light, ancient. Helium is the letter of quiet stability. Light, floating, and calm. Carbon is the letter of life's architecture. There will be more quiet stories about atoms, molecules, elements, water, fire, crystals, colors, and the hidden science of everyday things. You can also leave a like if you enjoyed this calm walk through the periodic table. It helps this little channel reach more sleepy, curious minds who might also enjoy learning softly before bed. And if there is a chemistry topic you would like to hear explained slowly, you can leave it in the comments. Maybe water. Maybe fire. Maybe carbon. Maybe the strange story of gold. Or maybe the chemistry of rain, clouds, and the ocean. But for now, there is nothing else you need to do. No more remembering. No more studying. No more trying to hold the table in your mind. You can leave the periodic table where it is. Quiet. Glowing. Patient. You can let the symbols become softer. You can let the names become distant. Hydrogen can become a small pale light. Helium can drift upward and away. Carbon can settle into the darkness like a quiet framework. Oxygen can move gently with your breath. Iron can rest deep and still. Gold can shine faintly, then dim. Neon can glow once, softly, and then return to silence. The whole table can become less like a chart now, and more like a constellation. Rows and columns of small sleeping stars. There is no need to count them. No need to name them. No need to understand all of them tonight. The elements are not asking anything from you. They are simply there. In the air. In the water. In the walls. In the earth. In the stars. In the slow chemistry of the world. And you can rest inside that world without needing to explain it. You can let the screen become softer. Let the elements drift away. Let the atoms keep moving quietly in the background. Thank you for spending this calm moment with gentle chemistry. If you are still awake, I hope the world feels a little softer and a little more interesting. And if you are beginning to drift away, let the elements become distant lights. Let the periodic table become a quiet sky. Let the rows and columns fade into darkness. And let yourself sleep. Good night.